Good afternoon, everyone. I am Amin Yazdani, Director of Canadian Institute for Safety, Wellness, Performance, hosted at Conestoga College. Our mission at CISWP is to improve the safety, wellness, and performance of the Canadian labor force by generating knowledge, transferring research to practice, and strengthening workforce development, all in collaboration with stakeholders. I would like to thank you for joining us today for this webinar. The format of this webinar is as follows. Presentations will be given, after which we have 15 minutes for questions. Please type your questions into the QA section of the webinar platform, and I will relay your questions to our presenters. The recording of this presentation will be available through CISWP YouTube channel within 1 week. Now, it is my pleasure to introduce our presenters today. Dr. Marcus Young is a research scientist at CISWP. He focuses on the etiology of work-related musculoskeletal disorders, exposure assessment, and development of prevention strategies and interventions to mitigate injury risk. He has expertise in individual-level measurement using biomechanical tools for both laboratory work simulation and field studies, and expertise in physical exposure estimation using population-level data to construct job exposure matrices. Mr. Bronson Du is a research scientist at CISWP and has expertise integrating human factors and ergonomic principles into industry-specific design standards and informing the development of national frameworks for work disability prevention and management. Mr. Du conducted multiple field studies in collaboration with seed manufacturers and trucking companies in Washington State, Connecticut, British Columbia, Alberta, and Manitoba to compare whole body vibration characteristics and their vibration attenuation capabilities of seating technologies and their impact on drivers. Now, I turn it over to Bronson and Marcus to provide the presentation. Thank you.
Hi, so good afternoon and good morning to all our listeners. So Bronson and I are very excited to speak with you today on some of our previous research that was completed in collaboration with faculty members from the universities of Saskatchewan, Waterloo, Washington, and British Columbia. So the subject of our webinar is whole body vibration. And whole body vibration is a ubiquitous physical exposure in many industries. It's also common in daily work in agriculture, mining, transportation, and construction. In today's presentation, we will demonstrate both field and lab approaches to understand the effects of whole body vibration on the health and performance of the worker. And we'll do this through a naturalistic study collecting vibration exposure over a workday in the transportation industry, as well as a well-controlled lab study on the acute effects of vibration at distinct intensities equivalent to current guideline thresholds. We will also examine the effect of an electromagnetically active vibration canceling seat, or EAVC, in reducing the impact of excessive vibration among truck drivers over a day in a work week. So we hope that our discussion today might generate better awareness and spur some ideas when reflecting on this physical exposure in different occupations. So what is whole body vibration? So they're essentially the shakes, the bumps, and jolts that are transmitted from the vehicle to the occupant. You might have heard of some possible benefits of vibration, and this is usually used for exercise and therapeutic reasons. But there's also strong evidence demonstrating the possible adverse health effects of vibration experienced in occupation. So what are the differences between vibration intended for training and that observed in occupation? They're namely due to differences in vibration intensity, vibration duration, vibration frequency, and the route and direction of transmission. So let's give an example. So let's focus on differences in frequencies. Occupational vibration is typically predominantly within the range, that being between 0 and 20 hertz, which matches the resonance of various body parts. So exposure to occupationally relevant vibration may affect the body in many different ways, both physiologically and biomechanically. There is evidence linking vibration to increased risk of low back pain, with studies demonstrating a dose-response relationship, as well as prospective studies demonstrating increased risk after multi-year follow-up period. There are other long-term health consequences associated with whole body vibration, and this includes hearing loss, gastrointestinal tract problems, neck problems, and spinal degeneration. It's also possible that whole body vibration has direct acute effects on multiple systems, leading to decrements in performance. So some lab studies using objective measures have shown decrease in wakefulness, as well as increased reaction times and vigilance lapses after acute exposure to vibration. On the other hand, lab studies using self-reports reveal conflicting results after acute exposure. Alternatively, it's been hypothesized that sleep disturbances are linked to vibration, where the intermediary effect is low back pain. So studies have reported a possible association between chronic low back pain and sleep disturbances. A meta-analysis indicated over half of the patients with nonspecific low back pain had sleep disorders, and this relationship may be bidirectional, and such that pain disturbs sleep, and sleep disruption is a possible modulator of pain. And this may lead to a vicious cycle of pain and sleep disturbance, where pain leads to a disturbed night's sleep, aggravating pain the following day. So just to summarize our last two slides, we find here that vibration may have both a direct relationship to performance deficits, but may also lead to performance deficits through a series of cascading effects, with low back pain, sleep disturbance, and daytime fatigue as intermediaries.
And so mitigating performance deficits due to fatigue is particularly important for people operating heavy machinery. Consequences of these performance deficits could result in serious injuries, fatalities, and significant economic burdens. So as an example, I'll talk a little bit about the impacts of fatigue on the trucking industry. So we know that driving while fatigued can be dangerous for the drivers themselves and for everyone who shares the road. But this is something that commonly occurs in the trucking industry. In a study by McCart and colleagues, they found that just under 50% of drivers have fallen asleep behind the wheel at some point, and 25% had done so in the past year. Another study found that 56% were tired at least some time while driving, and 32% had driven with their eyes closed. So the prevalence of fatigue in the trucking industry is quite high, and in Canada, driver fatigue accounts for about 750 collisions per year, so that's about 2 a day, and each cost a lot of money. The U.S. Department of Transportation says that a collision averages between $18,000 to $7.2 million, depending on its severity. Now, these statistics on fatigue-related incidents are based on police reports, which only considers extreme cases of drowsiness or falling asleep behind the wheel. So for an incident to be categorized as fatigue-related, there has to be no signs of skid marks, no maintenance issues with the truck, and good weather conditions with clear visibility. So this statistic is just the tip of the iceberg and does not account for any fatigue-related near misses that go unreported. All this to say, it's important to do whatever possible to reduce fatigue amongst heavy machine operators. If we look at the factors that can affect driver fatigue, there are individual factors such as circadian rhythm, sleep duration and quality, health, lifestyle, and there are health and wellness programs for drivers to promote healthy behaviors. There are also operational factors such as task complexity and monotony, time on task, rotational shift work culture, and allowed rest breaks. And an example of an operational intervention to improve drivers' alertness are laws that regulate how many hours a driver can drive and be on duty per day and week. And finally, there are environmental factors like weather, road condition, the cab design, and vibration. So there are many factors that affect driver drowsiness or driver alertness, but for our talk today, we mainly look at vibration while still considering other factors. Because of the many potential adverse health outcomes associated with whole body vibration, international guidelines and standards exist to provide consistency in measurement, evaluation, and the risk assessment of the exposure. There's 3 main guidelines and standards available: the British Standard 6841, the ISO 2631-1 and -5, and the European Union Directive that was out in 2002. And some of the common metrics used to describe whole body vibration are the average frequency weighted root mean square accelerations, which is used for describing constant magnitudes of vibration over a period of time. But if the exposure contains intermittent shocks and jolts, then the vibration dose value, or the VDV, is the preferred metric. So VDV is calculated as the root mean quad of the acceleration. And so this is more sensitive to peaks in acceleration compared to the root mean square acceleration. And the VDV is a cumulative value, so it increases with the duration of exposure. Often for comparing between exposures, the average weighted acceleration and the vibration dose values can be normalized to an 8-hour reference period, matching the duration of a workday. So they're also known as the A8 or the VDV8. So using these metrics, they can also be used to calculate other things such as the seat effective amplitude transmissibility, or the SEAT, which I'll describe later. All right, collecting whole body vibration exposure. I'll just go over how whole body vibration is collected in the field using our setup from 2 of the studies that I'll be talking about as an example. So what you'll need are some accelerometers. We usually use 2, one placed on the seat that's mounted in a seat pad and placed right under the driver's ischial tuberosity, and we put one on the floor. And when you're mounting, you want to make sure that the accelerometers are mounted in the right direction, so the axes are aligned. So the x-axis on the accelerometer is measuring fore and aft. The y-axis is measuring lateral accelerations, and the z-axis is measuring the up and down movements. From my experience of measuring whole body vibration in trucks, the z-axis has often been the predominant axis of exposure. We also mount another accelerometer on a rigid part of the floor close to the seat. And this is so that we can compare any differences in vibration measures between the floor and the seat to see how well a seating technology is reducing whole body vibration exposures. You might also want to collect exposures at the floor so that you can simulate the vibration profile in a lab setting. So both of these accelerometers, seat and floor, are connected to a data logger, which for us records at 1280 hertz. The frequencies that we are interested in are between 0.5 and 80 hertz, so you can probably get away with collecting a lower sampling rate. We also mount a GPS in the vehicle to collect speed and location. And with both the vibration and GPS data, we can sync them up in our program, and we can splice up specific parts of a route for standardized comparisons. So nowadays, cell phones have accelerometers and GPS built right into them. And there is a whole body vibration app that you can download and use as a simple screening or monitoring tool for whole body vibration. This app follows the ISO health guidance zones, and studies have shown that it's been quite reliable and accurate. For the remainder of our webinar, we'll be discussing 3 different studies. The first one will talk about collecting whole body vibration exposures in the field. Then Dr. Young will share his study on occupational whole body vibration guidelines. And lastly, I'll talk about an intervention study. All right, so the objective of the first study that I'll present was to evaluate the efficacy of 3 commercially available air suspension truck seats for reducing truck drivers' exposure to whole body vibration. And we were fortunate, very fortunate to have the opportunity to work with a trucking company that was very supportive of our research and was interested in reducing whole body vibration amongst their drivers. They allowed us to speak with their drivers, install different seats into their trucks, and conduct whole body vibration measurements. In this study, we measured 3 different truck seats. Seat 1 was the OEM seat that was already in the truck, and we measured it in 9 different trucks. And on average, these seats were about 12 months old. Now, seats 2 and 3 are both aftermarket truck seats available in North America, and they were brand new, serially installed and tested in the same truck on different days. So this trucking company, the trucks transported raw materials from 2 mines to a shipping port. So in terms of a regular day, the drivers would start their day at the base, drive with empty trailers to one of 2 mines to load it up using front loaders. And then once loaded, they would drive to a shipping port to unload and then return back to their base. So the entire trip was between 600 and 700 kilometers, depending on the mine that they drove to that day. And it took approximately 10 to 11 hours to complete. For each seat, we collected vibration exposures at the seat and the floor over the entire shift. And because we know that there's a number of factors that could affect whole body vibrations, such as terrain, vehicle speed, and driving characteristics, we have selected a standardized route for analyzing our whole body vibration data. So as an example of ensuring our exposure measurements were consistent across the seat comparisons, the data on the next slide represents a fully loaded truck that drove over the same paved 149 kilometer road segment. All right, so let's look at some vibration data. In total, we had 17 drivers who participated in our study, 16 in the first seat, 13 in the second, and we got 12 bums in the third. In this table, we present the A8 and the VDV8 of the predominant axis, which happens to be the Z axis of the floor and the seat measurements for seats 1, 2, and 3. And we also presented the exposure action values for the A8 and the VDV8. So if we look at the seat measure vibration value of seat 1, we can see that it's 0.55, which is above the exposure action value. But if we look at seats 2 and 3, we see that it's 0.43 and 0.44. And so this exposure would be below the exposure action value. We can also describe these seats attenuating, how well the seat is attenuating vibration by dividing the seat measured vibration by the floor measured vibration. So if we look at focusing on seat 1, we can see that the seat measured vibration was 0.55 and the floor measured vibration was 0.57. And so this equated to 0.96. So we can say that 96% of the floor vibration was transmitted through the seat into the driver's body, or the seat did a job of reducing 4% of the floor measured vibration. Now, if we look at seats 2 and 3, only 83% of the floor measurements were transmitted to the driver's body through the seat, or we can say that the seats did a job at reducing 17% of the floor measured vibration. So we can say that the type of air ride seat, the type of passive seat suspension did make a difference in exposure. And so seat selection is important. And so I just presented one study that measured whole body vibration, but there has been many other studies that measured vibration in various vehicles and machineries across several industries. In the figure on the left, we have some examples of vibration magnitudes standardized to an 8-hour day. And this was taken from the EU Good Practice Guide. And what we see here is that exposure fall between the ranges of 0.2 and 2 meters per second squared. And the typical exposure are above the action limit of 0.5. In the table on the right, the study by Can et al. Found that more than 50% of 67 operators were exposed to levels of whole body vibration that were above the standards for health risks. So the main takeaway from this slide is that whole body vibration exposures among heavy machinery operators often exceed current whole body vibration guidelines, and that whole body vibration exposures from different types of machinery in different industries generally fall within a range of vibration magnitudes.
And as Bronson mentioned earlier, there are some international standards and guidelines that have been developed for consistent measurement and evaluation. The same guidelines and standards are also a source for risk assessment, and this is through establishment of threshold values, limits, or action levels. So let's look at ISO 26031-1. This standard first requires that acceleration of the 3 orthogonal axes are frequency weighted when determining the probability of adverse health effects. Multiplying factors are then applied to the fore and aft and lateral and vertical axes, and often the axis with the highest root mean square magnitude is assessed. But if vibration in 2 or more axes are comparable, a vector sum is calculated, and this is used to estimate health risks. The exposure is then referred to the Health Guidance Caution Zone, or HGCZ. And this is used to estimate the probability of health risks. So the Health Guidance Caution Zone is composed of a lower and upper boundary, that being 0.45 meters per second squared and 0.9 meters per second squared for an 8-hour exposure respectively. The probability of health risks is interpreted by where the exposure falls along this caution zone. So for instance, if exposures were below this HGCZ, health effects are not clearly documented and or objectively observed. If exposures are within the zone, the standard indicates that caution must be had with respect to potential health risks. And if exposure is above this health guidance caution zone, health risks are likely. The EU adopted a physical directive, a physical agent directive, setting standards for the control of vibration across Europe in 2002. Given that the EU directive has an impact on health surveillance in Europe, with some countries considering introducing laws to limit vibration exposures, further investigations are required to better understand the acute effects of vibration using these guidelines. So the EU directive describes 2 threshold values, that being the exposure action value, or EAV, and the exposure limit value, or ELV. The exposure action value, if the exposure exceeds this value, the employer shall establish and implement a program to reduce to minimum exposure. The 8-hour reference period, or 8-hour reference exposure, is 0.5 meters per second squared. For the exposure limit value, if your collected exposure exceeds this value, the standard indicates that the employer shall take immediate action to reduce exposure below this value. And the 8-hour reference for the ELV is 1.15 meters per second squared. The EU also considers vibration containing mechanical shock, which are the transient forces that are of short duration and high amplitude. Mechanical shocks are defined as vibration that have crest factors greater than 9, and this is the ratio of the highest impact magnitude to the weighted root mean square. So the equivalent EAV and ELV for vibration containing mechanical shock are 9.1 and 21 root mean quad respectively. So when it comes to guidelines or standards for protecting workers from potential acute effects beyond those of low back pain and discomfort, unfortunately, there are no current guidelines. And as we mentioned before, there are a few studies that investigate the shorter effects of whole body vibration, but the direct transferability of this knowledge to the design of guideline thresholds are faced with several limitations. First, most available studies on the short-term effects are based on deterministic oscillatory motion vibration. Second, a number of these studies are also based off of vibration intensities and frequencies that are not occupationally relevant. Third, in most of these studies, the effects of vibration are often limited to a single domain, even though we recognize, as the name implies, whole body vibration, it might lead to multi-system effects. And finally, we need more controlled empirical studies to really tease out these potential dose-response relationships. So with these current research gaps in mind, the objective of this laboratory-based study was to investigate whether there was an effect of 60 minutes of vibration exposure at 4 different vibration intensities, and this was through a pre-test, post-test design, and to determine whether there are any differences in the effects between these vibration intensities based off of the EU Directive guidelines. So we recruited 18 healthy participants, 9 males and 9 females, with the following demographic characteristics. And each participant performed 4 conditions on 4 separate days with at least 24 hours apart between conditions. The presentation of the conditions were randomized on a per participant basis. We simulated signals based off of field data collected from ATV or all-terrain vehicle agricultural herding work, and we standardized the intensity of the vibration signal to the estimated total daily whole body vibration exposure of the sample population. So in this case, what we found was that the average ATV riding period was 2.43 hours of the population in which the ATV signal was derived from. We also adjusted the vibration signal inputs to account for the effect of participants' weight on the resultant vibration exposure at the CPAD by weight adjusting our simulated signals. So here's our 4 trials, or 4 conditions. Our control condition, which required participants to be seated while watching standardized TV programming. We had a low condition, which was based off the exposure action value, or EAV. And here you see the actual exposure of vibration at the CPAD, that being 0.938 meters per second squared. Our third condition was a shock condition, which contained transient impact forces superimposed above our EAV at 1-minute intervals. The resultant crest factor was 10.46, and the resultant vibration dose value at the CPAD was 13.49 root mean quad. And last, our high condition was based off the exposure limit value, and the actual vibration exposure at the CPAD was 2.129 meters per second squared on average across all participants. So in all conditions, participants were exposed to 60 minutes of whole body vibration while watching standardized TV programming. And to mitigate boredom and to remove unwanted ambient noise, they were given noise cancellation headphones. Participants were instructed to keep their hands on the handlebars at all times with their feet on the platform surface, and the predominant frequency along the vertical axis was 5 Hertz. So here we have some examples of our exposure profiles collected at the CPAD on the left, and to the right are just some sample videos. So I just want to draw your attention to some differences between our shock condition and our low condition, as well as our high condition and the low condition. So what you can see here is that there's transient impact forces at 1-minute intervals on the shock condition that's essentially superimposed on the exposure action value or the low condition. And then you can see the stark differences or the marked differences between the high condition and the low condition in terms of vibration magnitude. So for us to assess changes in the cognitive, sensorimotor, and physical systems, we collected a test battery of 9 measures immediately before and after each 60-minute vibration exposure. So I'm going to give you 3 examples of our measures. We measured rating of perceived headache and discomfort using a 10 centimeter visual analog scale with anchor points of no discomfort to maximal discomfort, and also 2 common measures of sensorimotor and cognitive function, that being postural sway and psychomotor vigilance task, or PVT. For postural sway tests, we had participants stand quietly with their feet at hip width and their arms at their front while gazing forward for 60 seconds. We collected the average root mean square of the center of pressure displacement in the anterior-posterior direction over that 60-second collection period. For the psychomotor vigilance task, or PVT, which is a 10-minute reaction time test that requires participants to react to a visual stimuli that appears at variable intervals, here we calculated both the average reaction time and also identified the number of lapses. And lapses were defined as reactions requiring longer than 500 milliseconds. So here we have some example results from our pre-post rating of headache and discomfort data. Along the horizontal axes are our 4 conditions: control, low, shock, and high. And along the vertical axis is our dependent measure. So in this case, it's the visual analog scale rating between 0 and 100 for rating of headache and discomfort. The black bars represent the pre-exposure value, and the gray bars represent the post-exposure value, or precondition or post-condition value. So we, to compare our pre and post values, we performed either a paired t-test or a Wilcoxon sign rank test for non-parametric responses. What we found in terms of rating of headache and discomfort, we found that both high and low conditions led to significant increases in headache and discomfort after exposure to vibration. So here we have our results for our postural sway root mean square amplitude values for our 4 conditions along the horizontal axes. And of course, on the vertical axis is our root mean square amplitude in the anterior posterior direction. So similar to headaches and head discomfort, we found significant increases in postural sway in the anterior posterior direction, again, after both low and high conditions. And finally are some results for our PVT responses. So to the left is mean reaction time, and to the right is the median number of lapses. So for mean reaction time, we observed a significant increase in reaction time after exposure to the high whole body vibration condition when compared to its baseline values. Since the number of lapses was found to be non-parametric, we applied the Wilcoxon sign rank test, which revealed significant increases in the number of lapses after exposure to the high condition. And to determine whether there were any statistical differences between conditions, we normalized our post value to its pre-value and applied these calculated values as the dependent measure in the mixed model repeated measures analysis with Tukey-Kramer post hoc tests. After that calculation, we found that there was a significant difference between high and control conditions. So just to summarize on the basis of each condition, for the control condition, we identified and observed significant increases in upper body discomfort. For the low condition, we observed upper body discomfort, as well as increases in headache and discomfort, postural imbalance, but the effect on cognitive functioning was less clear, and this was due to some discrepancies between our cognitive measures. For the shock condition, we observed whole body discomfort, but the remaining variables revealed no significant effects. And this may be due to the high variance as a result of different adjustment strategies to sudden perturbation. And finally, in our high condition, we observed whole body discomfort, increases in headache or head discomfort, increases in postural imbalance, and clear decrements in vigilance. So just to summarize the overall study, we found that whole body vibration did not induce additional effects beyond those for sitting without vibration. Whole body vibration may not necessarily be the only source of observed acute sensorimotor or cognitive effects. However, we did find that the pre-post effect did increase with increasing vibration intensity. And I think this has some implications on both the interventions and action controls, as we should address both prolonged sitting and whole body vibration. And the fact that current international guidelines may not be sufficient to reduce acute sensorimotor and cognitive vibration effects. So for future work, there remains a need to understand the dose-response relationship. But for now, what we know is that excessive whole body vibration is problematic. So I want to draw your attention to a quote from Michael Griffin in 2003, who is a preeminent expert in this area. He indicated that the quantitative guidance is insufficient to identify vibration hazards, but really it's the qualitative guidance, which is reducing the risk to a minimum. That's the key message.
All right. So for controlling any type of occupational hazard, including whole body vibration, we like to use something called the hierarchy of controls. And the idea behind this hierarchy is that control methods at the top, elimination and substitution of the hazard, are potentially more effective than those at the bottom, like administrative controls and personal protective equipment, which may require some form of behavioral change. So elimination and substitution are most effective at reducing hazards and tend to be most difficult to implement into existing processes. So these methods should be applied in the earlier stages of design. And in the case of whole body vibration, it wouldn't be possible at this point. Engineering controls aim to remove the hazard at the source before it comes into contact with the worker. So for exposures to whole body vibration in heavy machinery operators, this could be things like superior suspension systems, either for the truck or the seats. Administrative controls can be things like reducing the duration of vibration exposures through scheduled breaks or increased maintenance of the machinery. And an example of PPE or personal protective equipment could be an anti-vibration seat cushion. And so for the next study that I'm going to talk about, we're going to focus on an engineering control. It's a newer type of seat suspension that actively cancels out vibrations of the floor. And it's been shown to reduce the floor vibrations by 55% compared to the 17% of the passive air ride aftermarket seats that I showed you in the earlier study. So there was a lot of interest in this new ability to significantly reduce whole body vibration in the field amongst truck drivers. And so we conducted a small field study to, one, determine if these vibration canceling seats affected vigilance over the course of a workday and the work week. And we also wanted to determine if the drivers found the vibration canceling seat comfortable. So just looking back at our causal diagram and how whole body vibration could impact performance either directly or through a cascade of intermediaries via low back pain, we wanted to see if there's any significantly reducing whole body vibration exposures at work could actually have any real world impact on performance despite the causal route. So to fulfill the purpose of the study, we worked with a seat manufacturer and a trucking company to help us recruit drivers who have never driven in the vibration canceling seat before. We were able to recruit 5 drivers to participate in a repeated measures crossover design. So we measured vigilance and discomfort immediately before and after the driver shifts over 2 weeks. The first week, was to collect a baseline measurement of the drivers using their existing passive air suspension seats. And then we worked with their mechanics to kind of switch out the old seats and replace it with the active vibration canceling seat for a second week of collection. So overall, we measured 50 workdays of vigilance and discomfort, and we measured floor and seat vibration exposures for each of the drivers in both seating conditions. Just to recap, the independent variables for the study were the two different seat types, the existing passive air suspension seats that were already found in the driver's truck, and the vibration canceling seat that was installed afterwards. Time was also a factor. We looked at change over the course of a work day and over the course of a work week. For our dependent variables, we measured whole body vibration, and the metrics that we used were the A8 and the VDB8. We also used the psychomotor vigilance task that Marcus used in his study. And in addition to the mean response times and the number of lapses, we also measured the fastest and slowest 10% response times, the variability of their response times, and the reaction speed, which was the inverse of the reaction times. For discomfort, we used a 10-point discomfort scale over 8 different body parts. All right, so let's look at some of the participant demographics. The participating drivers had a mean age of 54 years old with a BMI of 36, which is classified as obese. And all drivers were experienced drivers, having worked at least 16 years in the trucking industry. And they've been with the company for at least 1 year. They also reported working between 45 to 65 hours per week, with 90% of the time spent driving. All right, so this table just shows that the drivers had similar work and lifestyle habits between the two different work weeks of that we collected data over. So they were similar in the duration driven, the distance driven, their sleep duration, and caffeine intake. Let's look at some of the results from the whole body vibration exposures. Here on the vertical axis, we have the A8 showing the Z axis measured in meters per second squared. And on the horizontal axis, we have the floor and seat measurements for the passive and active vibration canceling seats. So if we look at the black columns first, we can see that the seat vibration is lower than the measured at the floor, measured at the seat than on the floor, meaning that this seat did some work at reducing vibration. The active seat, represented by the blue columns here on the right, did a significantly better job at reducing vibrations from the floor. It reduced exposures by about 55% and brought the exposures to about half of the action value. So the takeaway from these slides is that both exposures were below the exposure action value, but the whole body vibration exposures from the active vibration canceling seat was significantly lower, almost half of, over half of the action value limit, action limit. So let's see what that does, how that impacts vigilance over the course of a workday. In this graph, we have the response times on the vertical axis, measured in milliseconds, and on the horizontal axis, we have the time of day, pre-shift and post-shift. So we see that mean reaction time is slower at the end of the day for both seats, which makes sense. But with the vibration canceling seat, the mean reaction time did not slow down as much as the passive air suspension seat. And we also saw this finding for the fastest 10% reaction times. There were also similar trends for the other PVT metrics, but not significant. So it is important to note that our driver participants had regular work schedules and were not sleep deprived. So it makes sense that we only saw significant differences in PVT metrics that looked at peak performance, like the fastest 10% reaction time. All right, so if we look at over the work week, we see that, well, although these results were not significant, we did see a trend that on day one, after 2 days off or after the weekend, PVT performance for the mean reaction time and the reaction speed were the same. But on day two, for the existing seat, there was an increase in mean reaction time and a decrease in reaction speed, and it remained there for the rest of the work week. However, the performance was more consistent in the vibration canceling seat. So perhaps 1 night of rest is not enough recovery time for vibration levels that were close to the action limit. From the pain and discomfort survey, we saw increases in discomfort in the low back and the wrist and forearms over the course of a workday in the existing seat, but not in the vibration canceling seat. And we had kind of expected this for the low back, but for the wrist and the forearms, that was a surprise to us. And we think that the increases in wrist and forearm discomfort over the shift was from needing to hold on to the steering wheel tighter to stabilize the body when the vibration levels were higher. So to summarize, the active vibration canceling seat did effectively reduce 55% of the floor measured vibration from being transmitted to the driver compared to 8% reduction of the truck's existing passive seat. And both seats that we measured, the exposures were below the exposure action value, but there was a significant difference in the exposures. We also saw a reduction in the decrements of PVT performance over the course of a workday in the vibration canceling seat. And there was a trend of decreasing PVT performance over the course of a work week in the existing seat. We also found that there was a reduction in discomfort in the low back and wrist and forearms over the course of the workday in the vibration canceling seat. So there were some limitations with this study, but first I want to say that this was the first study of its kind to manipulate whole body vibration exposures in the field and measure its effect on vigilance over the course of a workday and work week. Since this was a within subject crossover study design, individual factors like general health, well-being, and lifestyle habits, operational factors like schedules, routes and duties, and environmental factors like the cab design were similar, if not identical, between the two conditions. But there were some limitations to this study. The PVT cannot be assessed while driving. So we only assessed before and after, and we weren't sure what happened during the shift. And so future studies can look at, there's new technologies now, and future studies can look at looking at forward-facing cameras that measure lane deviations to look at performance. The study, there was also no randomization of the conditions, no blinding of the conditions, and there were 2 different seat tops. So, but this was something that was difficult to control due to logistics for us. There was also a low sample size, but we still were able to see some significant difference in vigilance and performance. So we did have enough power for that. And lastly, before we close off, we wanted to share some additional thoughts. Although active suspension seats are effective, they are expensive, almost 10 times more than the passive air ride seats. And there are some new passive seats, suspension technologies that are almost as good as the active suspension seats now. It also doesn't address the prolonged sitting. So other risk mitigation strategies like work scheduling should be considered in combination with the seating interventions. So that's the end of our presentation. I would like to take the opportunity to once again thank our funding sources, our research collaborators, industry partners, research participants, and you, the audience, for taking the time out of your days to join us on the webinar. So at this point, we would like to turn our presentation over to Dr. Yazdani and welcome any questions from the audience.
Thank you, Bronson and Marcus, for your great presentation. We have a question for you, Marcus. You indicated that you adjusted your simulated signals by participants' weight. Why did you weight adjust your signals?
Yeah, that's a great question. So let me just clarify first. We had some simulated signals that we actually input into our 6 degree of freedom hexapod. And we did our weight adjustment to ensure that there's some consistencies in terms of the level of exposure for each participant. So I'm reminded actually of a field study in 2011 or so by Manny, who found that body mass was actually significantly but negatively associated with whole body vibration exposure. And this was done among ATV riders while controlling for extrinsic vibration factors like the ones that Bronson described, like riding terrain, vehicle type, and driving speed. And what they found was that among all intrinsic factors like driving experience, age, and height, body mass was actually found to explain up to 38% of the variance in whole body vibration exposure. So when you interpret this, this means that the heavier your body mass, the lower vibration exposure at the seat pad. And this is actually consistent with some lab studies. One comes to mind is what was described in Neil Mansfield's work, indicating that the influence of body mass on whole body vibration exposure is associated with aspects of mechanical impedance, absorbed power, and transmission in apparent mass. What's also very interesting is that in occupational epidemiology studies, what they've shown is that in the prediction of risk of low back pain, participants exposed to whole body vibration who also had high BMI, they actually didn't increase the risk. These two in combination did not increase the risk of the development of low back pain. So quite possibly the influence of body mass as conceptualized by Manny may explain why body mass did not seem to increase the risk of low back pain in professional drivers. So maybe taking all this into consideration, we had to take into account participants' weight and adjust our incoming simulated signals in order to minimize their influence on resultant vibration exposure and to standardize the exposure across participants for equitable comparisons.
Okay, thank you. Thank you, Marcus. Bronson, both the lab and field studies use this PVT reaction time measure. And in the field study, the differences look very similar. But you said that it was significant. Is there any real world implications on driver performance?
Oh yeah. That's a great question, Amin. Thanks for the question. Yeah, so the differences that we found in our study, the differences in the decrements, let's say for the mean reaction times, comparing between the active and the passive seat, that difference was about 14 milliseconds. So it does look like quite small, right? 14 milliseconds. But this could have some this could be potentially important for making driving related decisions, this 14 milliseconds. So I know there's been some lab studies that also use this PVT task, and they also used the like a simulated driving simulation to look at lane drift incidents. And what they found was that a 15-minute increase in reaction times was correlated with decreases in driving performance by almost doubling the amount of lane drift incidents. And this was a non-sleep deprived participants. The participants were non-sleep deprived. So it's also important to note for us that this PVT is a sustained attention reaction time task where participants are only required to respond to one stimulus by pushing one button for just 10 minutes, right? But reaction times can significantly increase when there's multiple stimulus and multiple response options. So in the real world settings, for drivers, for example, they must recognize and process like more information on the traffic, road, weather conditions, and how to respond appropriately, either through lane tracking, accelerating, or braking. So, and they do this for a prolonged period of time, 10 to 11 hours as opposed to 10 minutes. So as a result, the 14 millisecond difference between the two seats might have some significant implications for driving performance and road safety.
Okay, well, that's very interesting. Thank you, Bronson, for that comprehensive answer. And on behalf of our team here at CSWP, I would like to thank you all for joining us today. We hope to see you in our future webinars. For more details about our complimentary webinars, please visit our website. So again, thank you for our presenters today, and hope to see you all soon again. Have a wonderful day. Thank you.